Good morning. My name is Lakshmanan and today we shall be discussing the versatility of Charpy's test to accommodate specimens of different sizes. Out here we can see a standard Charpy's test. Now, a Charpy's test is a test which is conducted to analyze the impact resistance of the material. In this setup, the specimen is kept in a vertical direction and held by supports out here, and a V notch is induced into the specimen, which faces the direction of the striking edge. Now, the striking edge of a minimum capacity of 250 joules and a striking edge radius of 2 millimeters used. It is attached to a pendulum which is then connected to a scale which reads how many joules of energy is used to break the specimen. On analyzing the amount of energy that is used, we can determine the impact resistance of the material. Now, in the industry, Charpy's test is usually used to find out how much pressure or how much stress or strain the material can handle before it fractures. So, certain applications are like pipelines in the industry, and this is a very important application for the Charpy's test, as it's very imperative that the pipelines don't fracture upon its use. This is because sometimes the pipelines carry oil and natural gas, and on rupturing it could be really hazardous. Hence, we must find sometimes specimens of the standard size, that is 10 into 10 into 55 millimeters, are not available for testing, or the specimens do not come in that size as the thickness is less than the minimum required thickness, that is 10 millimeters. Hence, in such conditions, we have to use a modified method or a different, a certain calculation that helps us correlate the data between the smaller or the bigger specimen and the standard Charpy specimen. So, there already exists certain amount of correlational methods, that is the Buttle's two-curve method, the Buttle's short formula, the Gerson, Dweigard, Needleman's model. Then we've got methods that relate the transition temperature and upper shelf energy of the two types of specimens, and also the fracture arrest transition temperature. Now, out of all these methods that exist, I feel that the Buttle's short formula is the most convenient and easiest way to correlate the data. But in order to understand Buttle's short formula, we must first understand Buttle's two-curve method, as the short formula is derived from the two-curve method. Now, the two-curve method, in this method, they basically consider the driving force for ductile fracture propagation, and this is uniquely related to the gas pressure in the phase of the crack tip. It is based on the principle that the occurrence of the full bore opening in a pipeline, when the full bore occurring in a pipeline, the internal pressure does not immediately drop to zero, as the gas escape velocity cannot exceed the acoustic velocity. Hence, in order to determine the decompression velocity, Buttle came up with a closed form solution which shows the relationship between the decompression velocity within the expansion wave and the pressure, which is given by this formula. In it, PD represents the decompression pressure, PI represents the initial pressure, gamma represents the specific heat ratio, V represents the velocity of propagation of pressure, and VA represents the original acoustic velocity. Now, the fracture velocity can be determined by a two-part equation. The first equation determines the arrest pressure, and the second equation determines the fracture velocity. In the arrest pressure equation, sigma A represents the arrest pressure stress, sigma dash represents the material flow stress, R represents the fracture propagation resistance, E represents Young modulus, D and T represent the diameter and thickness of the specimen, and out here VF represents the fracture velocity, sigma dash represents the material flow stress, and P represents the internal pressure, and PA represents the acoustic pressure. The exponential value x is represented by is taken as 1/6 1 by 6 when R is equated for Charpy's shelf energy per unit area. Now, the relative position of the fracture and decompression velocity curves determine whether ductile fracture will be arrested or will continue. This graph shows the relation between the decompression fracture velocity and the pressure. This line represents the operating pressure, and as we can see, toughness increases as the curve size reduces. Here we can see that for a constant pressure, the decompression and fracture velocities keep increasing up to a certain point, after which it stagnated for increasing pressure. This helps us determine whether the ductile fracture will be arrested at a certain pressure or will continue to propagate. Now, based on this, Patel came up with another easier equation, which is called the short formula. This is done because the earlier method, the two-curve method, was tedious, and it was basically tough to calculate the arrest pressure and to figure out the propagation of the fracture. So, and it was also limited to 2/3 of the specimen size. It wasn't for all subsize specimens. Then a short formula was developed, and this is basically it compares the data between the formula which is generated out here and the two-curve method to figure out the accuracy. Now, this equation is basically, it comes from the two-curve method. It shows the arrest toughness of the material, and it includes a broader range of variables, that is the hoop stress, the diameter, the thickness of the specimen, and the acoustic velocity. Now, this can be verified by simply applying the value of acoustic velocity, that is 396.34 meters per second, and it gives this equation, which is one of the equations in Butter's two-curve method. Now, since this short formula was created by correlating the TC, and that's the two-curve method, and the data from the formulas which have been obtained from the short formula, and a scatter graph is created in order to see the accuracy of it. Now, 1749 results have been produced in this scatter graph, which compares the arrest toughness from the two-curve method and the arrest toughness from the short formula. Out of these 1749 results, 785 are within a difference of 1 joule of arrest toughness, 1284 results are within 2 joule of toughness, 815 are within 2% difference, only 162 results are outside 5%, and only 29 results are outside 10%. Now, the 29 results which are outside 10% difference are for specimens that are less than 2.5 millimeters. Now, the advantages of this short formula is that it is very easy to use. It is accurate for specimens of minimum thickness of at least 2.5 mm, and the correlation can be easily and quickly calculated. The disadvantages of the short formula is that the accuracy drops if the thickness reduces below 2.5 millimeters, and that the method is slightly outdated because it has been replaced by modern models which are there in computers, which help calculate the data for all sizes. But the thing that's fascinating about the short formula is that even though it is outdated, it is still used as a standard in many of the industries, which makes short formula one of the best and longest lived method for calculating and correlating the data between different size specimens. And this is the method I use to answer my research question. Thank you so much.